Welcome to Maths with EJD, and we are still on the subject of mathematical induction. So in this video, our problem is what you have on the screen, which can also be stated as this to show, want to show that 10 raised to power 2n minus 1 plus 1 down here is divisible by 11 for all natural numbers. For all natural numbers. Show that 10 raised to power 2n minus 1 plus 1 is divisible by 11 for all natural numbers. So you know our regular process. You state the claim. You state the claim. So the claim here is that 10 raised to power 2n minus 1 plus 1 is divisible by 11 for all natural numbers, for all natural numbers. That's the claim. Okay. And then we have um the base step. The base step, that is where you use the smallest values of n, starting from that is 1, to check. So here at n equals 1, we have 10 raised to power 2, 1 minus 1 plus 1. That is 10 raised to power 2 times 1 is 2 times minus 1. That is 1 plus 1. That is 10 plus 1. And that is 11. And 11 is 11 multiplied by 1. So that works. Okay. So we go again at n equals 2, which is not necessary, like I always say, but I just like to do that. So you have 10 raised to power 2 times 2 minus 1 plus 1. And that is 10 raised to power 4 minus 1. That's 10 raised to power 3. 10 raised to power 3 plus 1. And 10 raised to power 3 is 1,000 plus 1. So that is 1,001. 1,001, which is 11 into 11. 1,001 divided by 11. I think that is that 11 times 99 or something? Looks so simple. Let me be sure of that. I think it should be 99, right? Let's see. Let's be very sure. So 1,001 divided by 11. Okay. That is 91. Okay. So that's 11 times 91. 11 times 91. So which is also fine, right? So that's about the base step. So let's talk about the inductive hypothesis. Inductive hypothesis. So for the inductive hypothesis, again, we assume, assume, assume assume the claim is true. Assume the claim is true for n equals k. So if that is to be assumed, then it means that 10 raised to power 2k minus 1 plus 1 is equal to 11 times q, if you like that. So 10 raised to power 2k minus 1 plus 1 equals 11q. And just like you always know, this expression is very helpful for you at the inductive step where you do the final proof. So you want to pay attention to it. It may come in handy. So let's see how that works. So at the inductive step, what do we get? We want to prove that the claim that the claim is true, that the claim is true for n equals k plus 1. And how does that go? So it means that for where you have k or n here now, it should become k plus 1. So you have 10 raised to power 2 into k plus 1 minus 1 plus 1. And that is equal to 10 raised to power 2k plus 2 minus 1 plus 1. And that is equal to 10 raised to power 2k. Okay, well, I may want to do something. So I may want to replicate something here. Okay, if we work on this, right, we can say 10 raised to power 2k minus 1 is the same thing as 11q minus this one down here, right? So we can say that. So we can say this is 10 raised to power 2k minus 1 times 10 raised to power 2 plus 1. You can see this 10 raised to power 2k minus 1. Then the, okay, let me not jump. Let me show it as it's happening clearly. So this is 10 raised to power 2k minus 1 plus 2 plus 1 down here. So I just want to leave that way. So you have 10 raised to power 2k minus 1. From the law of indices, we can say this is multiplied by, okay, let me just do the multiplication thing. So you have multiplied by 10 raised to power 2. You know, indices still makes that work plus 1. So this is more like 10 raised to power 2 into 10 raised to power 2k minus 1 plus 1. And from the previous situation, right, 10 raised to power 2k minus 1 is 11q minus 1. So we can come here and say that this is 100, 10 raised to power 2 is 100 into 11q minus 1 plus 1, all right? 11q minus 1 plus 1. So we have 100 times 11, that is 1100 or 1100 q. 100 minus 100 times 1, that's 100 plus 1, right? So we have 1100q minus 99. Okay, minus 100 plus 1 is minus 99. And we can factorize 11 out of here. So we have 11 into 100q minus 9. So obviously 11, so you can factor out 11 here. And that gives us a very nice place to make comments. So, you know, we can say, therefore, the claim is true for the inductive step, for the inductive step. The claim is true for the inductive step. So, and since it is true for the inductive step, we can make the overall claim, with the overall conclusion that it is true for all positive integers or for all natural numbers, okay? Natural numbers are positive integers, right? So, um, so the claim, of course, you know what the claim is, but since we've named it already, you can just say the claim is true for all natural numbers, for all natural numbers, since since it is true, since it is true for the base and inductive steps, for the base and inductive steps. So on this note, if you have not subscribed, make sure you do that and hit the notification bell so you can get alerted whenever a new video is released. Like and share. I know a lot of people will find this very useful. Then of course make comments if you want us to solve any problem, you want me to treat a topic, or you have any recommendation for me to make what I do better. I'll be very glad. I've got very helpful recommendations from viewers, and I'm very grateful always for those. Thank you so much. Keep them coming. See you in the next video.